with a complement to 1.5, so what we have done yesterday at the end. And in fact, it is an application of the description we gave of the spectrum of a data algebra in one variable. So it works over an arbitrary non-Archimedean field, but to fix ideas, I will pick CP, the field of complex p-adic numbers, which is a completion of an algebraic closure of QP, which is algebraically closed, and whose residue field is an algebraic closure of FP. So recall what we have done yesterday. So for A, an element of absolute value at most 1, and R, a real number between 0 and 1. So we denote it by E of AR, the closed disk of, so let's call it, so X will be the spectrum of the Tate algebra in one variable of a CP. So E of AR is the set of all points in capital X, such that the absolute value of T minus A at X is not greater than R. So it's closed disk. And we have a similar definition for an open disk. We just put a strict inequality. So this is R. This is open disk. So in X, we have a distinguished point, which is the Gauss point. It means the point which corresponds to the Gauss norm on this algebra. And if you remove this point from the spectrum, what you get is a disjoint union over which is parameterized by the points in the residue field. So element of an algebraic closure of FP of disk of radius, open disk of radius 1, where sigma is a section of the reduction map modulo the prime ideal, sorry, FPA. Okay, and last thing which we will use, each neighborhood of eta in X contains a subset of the form. So what you do is you remove from X a finite number of open disks with radius strictly less than 1. So X minus some open disk D of AI Ri with AI in the integer ring, and Ri between 0 and 1 strictly. So this is a fundamental set of neighborhoods of eta. And the proposition I will prove now is the following. Any injective sequence of roots of unity in CP converges to the Gauss point eta in X. So when I have a root of unity, it is an element of the field which has absolute value 1. So I can see it as a point in X. And since X is compact, I can look at convergence to subsequence. And in fact, the whole sequence converges to the Gauss point. So the proof is the following. So I will prove that such the complement of such a set cannot contain more than a finite number of roots of unity. So let's call it V. So it is enough to prove that so the complement is a finite union of open disk with radius less than 1. So it is enough to show that any open disk with radius less than 1 contains a finite number of roots of unity, contains only a finite number of roots of unity for any A in CP0 and R between 0 and 1 strictly. So pick a root of unity, psi. So if it belongs to such an open disk, then its reduction modulo the maximal ideal of CP0 is the reduction of A, which is the same thing, in FP, algebraic closure of FP. So the order of psi is a power of P times the order of the reduction of A in the group of invertible elements of the algebraic closure of FP. And what now you have to do is to show that this power of P is bounded. Okay. So up to multiplying psi by a root of unity which reduces to the same thing, you can assume that A is 1. And now what gives you the conclusion is the fact that you know how to compute the absolute value of a root of unity. Say what you ask is any p to the nth root of unity say has absolute value bounded by, so the absolute value of p to the 1 over p to the n minus 1 times p minus 1. This is a classical computation. So if you if you plug in, what you get is that this number, capital N, is bounded by logarithm in basis P of minus 1 over P minus 1 times logarithm in basis P of R plus 1. So there's only a finite number of possibilities for. Sorry? This is the p-adic absolute value. So the absolute value of P is 1 over P. What is the question? Ah, sorry, yeah. Yeah, sorry. Okay. Yeah, of course. Sorry, you're right. What you want to see is that you want to control the radius, which is the distance of psi to the center of the disk. So you has distance to 1. Bounded by. Okay, so this implies that. Okay. Yeah, sorry, I was too quick. The distance to the. So the radius of a disk which contains 1 and such a root is controlled by the order of the root. Above. The distance is at most below by 0. I mean, you. The distance is bounded above. It cannot be okay, so let me rewrite it. Yeah, so what I want to say is, okay, yes, I can say that. Okay, all right. Sorry, so I will. Yeah. Okay. So any primitive, you're right. P to the nth root of unity has distance to 1 equal to okay, so what it means is that the distance to 1 goes to 1. So this distance goes to 1 when n goes to infinity. Okay. So if you fix a radius which is strictly less than 1, you cannot have more than a finite number of roots of unity. So this implies that n is bounded. Okay. So this is the correct formulation. So what it shows is that you have you can make sequences converge in this those spectra in Berkovich spaces, and this is a very elementary example of what happens when you want to do non-Archimedean dynamical systems. You want to look at behavior of sequences and so on, and this can be done quite efficiently in the framework of Berkovich geometry. So comment. One can apply Berkovich geometry to develop non-Archimedean dynamics. Okay, so this was an example of what one can say once one has understood a little bit of the structure of Berkovich space. So now I will move to the second part, which is devoted to the structure sheaf on the spectrum. So our goal is to define a sheaf in some way to be able to glue together spectra. So let me first say a few words about the so-called spectral seminorm. In fact, this is something very important I should have said before. So let A be any Banach K algebra. Recall that for A in A, you define the spectral radius, rho of A, as the infimum of the nth root of the norm of A to the n, which is also the limit of this sequence. This is the spectral radius. And this has a nice interpretation in terms of the spectrum M of A. Proposition. For any f in A, the spectral radius of f is nothing but the maximum of the absolute value of f at points of the spectrum. And from that you can deduce, which was not obvious a priori, that the function rho on A is a seminorm, namely rho of f plus g is not greater than the maximum of rho of f rho of g, and rho of fg is less or equal to rho of f times rho of g. In general, it is not multiplicative, it is only submultiplicative. This is obvious with this property. This is absolutely not clear from the definition. And what you can, so for any Banach algebra in general, you have this semi-norm, but it's not clear that you can compare the norm given on A and this semi-norm. What you can look at is the subset A0 of A, which consists of elements which have bounded powers, so the sequence of powers is bounded. This is K0 subalgebra of A. And of course, if you have such a property, when you compute the spectral radius, you find that it is at most 1. So, of course, A0 is contained in the subset defined by the condition O is less or equal to 1. And in general, this is only an inclusion. And in fact, this is an equality. If and only if the following property holds. What is the property? Is that you can control the norm of an element in terms of its spectral radius. So for any f in A, there is a constant such that the norm of f to the n is less or equal to c times the spectral radius to the n for n big enough. So if you have a control of the norm in terms of the spectral radius for all large enough powers, then you have equality, and this is an equivalence. And maybe you remember that I mentioned this property in the first talks. Namely, if A is a k-affine algebra, then this is true. This is not that easy to prove. And in particular, you have equality here. So what we will say, this is not a standard terminology. We say that A is good if this property holds. And as example of good binary algebra, you have so non-Archimedean field. This is obvious because the absolute value is the spectral semi-norm. And also you have k-affine algebra, which is less obvious. And in what follows, I always deal with binary algebras which are good. It means I can, in particular, deal with k-affine algebras and arbitrary field extensions. Okay. So now we really start the process to define the structure sheaf. And what we will do is to distinguish inside the spectrum of an affine algebra some particular subsets to which we can attach some algebras. So they are so-called affinoid domains. So let A be a k-affinoid algebra. And as I said, our motivation for the following definition is to attach some k-affinoid algebras to some distinguished subsets of the spectrum. So it's why I introduced the following definition. So if you have any subset of M of A, say let's call it V, well, you can define a functor on the category of all good binary algebras in the following way. So any subset. So consider the following functor fv, which goes from the category of all so good, I said it is implicit in everywhere, good binary algebras to the category of sets, and which maps binary algebra B to the set of all homomorphism of binary algebras from A to B. Sorry, so the set of all homomorphism which satisfy a condition. So all homomorphism from A to B, U, such that when you have such a map, you can look at the induced map between the spectra, which goes from M of B to M of A. This is the so-called associated map AU from M of B to M of A. And you require that the image of this map is contained in V. Maps into V. So you look at all binary algebras B which have a morphism from A, whose image, when I go to the spectrum, is contained in V. And by definition, so we say that V is an affinoid domain if this functor is representable by a k-affinoid algebra, if f of v is representable by a k-affinoid algebra AV, which as a solution of this universal problem comes with a morphism from A to AV, equipped with a morphism say phi V from A to AV. So if this functor is representable by a k-affinoid algebra, we say that V is an affinoid domain. So as by general nonsense, you know that if this is the case, then the algebra and the morphism are unique up to unique isomorphism. So if V is an affinoid domain, then the pair AV phi V is unique up to unique isomorphism. So there is an algebra attached to the subset. And in fact, the spectrum of AV is exactly V, which I will prove immediately before giving you some examples. So the position. So let V be an affinoid domain the map associated to the morphism phi v, which goes from the spectrum of AV to the spectrum of A. This map, I say, is a homeomorphism onto V. So let us prove it. So we have a continuous map between two compact Hausdorff spaces, so it is enough to show that it is a bijection. So it suffices to prove that phi v is a bijection. And as you may imagine, this is an easy application of the definition as a solution of a universal problem. Namely, if you look at morphism from AV to any non-Archimedean field extending small k, so for any non-Archimedean extension capital K of small k, what is the set of homomorphism of binary algebras between AV and capital K? By the very definition of AV, this is the set FV of capital K, which is to say that this is the set of all homomorphisms from A to capital K, such that the image of the associated map is contained in V, but the spectrum of a field is a point. So this is only to say that you have a point X in the spectrum of A, which belongs to V, and an embedding of its completed residual field into capital K. So this is the set of pairs X iota, where X belongs to V, and iota is an embedding of the residual field of X into capital K. So what you see here is surjectivity, because you pick any point, you let capital K be the completed residual field, then you have defined a point, an element here, which corresponds to a point in the spectrum. So surjectivity of the map is now obvious. What about injectivity? Well, if you have two so remember that I described the spectrum as the set of all bounded homomorphism between the algebra and an arbitrary non-Archimedean extension of the field, modulo some equivalence relation. So I look at two such homomorphisms. So U from AV to K, and U prime from AV to K prime. defining the same point in V by composition with this map. So if I have two such morphisms which are over the same point in V, which is to say that they define the same morphism when I compose with this map, I want to show that they define the same point in the spectrum of AV. Then they define the same point in the spectrum of AV. Why? Because we have a commutative diagram where U second is U double prime is what? Is a map I get by looking at the tensor product of capital K and capital K prime over the common ground field H of X. This is non-zero, so I can find a map to common extension of capital K and capital K prime. So we have a commutative diagram obtained by considering a morphism from capital K tensored with capital K prime over H of X, which is non-zero, to non-Archimedean field capital double prime, K double prime. So they define the same point in the spectrum by the description in terms of equivalence classes. Okay, so let me just state two facts about affinoid domains, or maybe I will give first an example to show you that this is quite, one can construct such subsets quite explicitly. So example, so let A be a K-affinoid algebra. So X is its spectrum. I want to describe explicitly affinoid domains in X. So I can do this in the following way. I pick some functions in A, say f0, f1 to fn, which I assume to be without a common zero in X. Which is to say that they generate a the ideal they define is A. So they generate A. And I consider the subset V defined by the following. I pick some real numbers. So let R1 to Rn be positive real numbers. And consider the following subset V. Consider V. So what is V? It is the set of all points in X which are defined by inequalities between our functions. Namely, so f1 of x is less or equal to r1 times f naught of x, and so on. Fn of x is less or equal to Rn f naught of x. And what is easy to check is that V is an affinoid domain. I can give you explicitly the corresponding affinoid algebra. Corresponding to the algebra AV, which is a quotient of the Tate algebra with coefficients in A and polyradii, the I's. So R1 minus 1 T1, Rn minus 1 Tn. So a Fermat power series with coefficients in A, which, so to speak, converges on the polydisk of polyradii R1 to Rn, mod out by the ideal generated by the following relations. So f1 minus f naught T1, and so on, fn minus f naught Tn. So what you have done formally, you say that you have added functions which represent the quotient f1 over f naught, f2 over f naught, fn over f naught. Those are the TIs. And this should remind you of the formula you see when you define blow-ups in algebraic geometry. And tomorrow I will explain that this is really a blowing up if we look at it from the right point of view. Okay, so such affinoid domains have a name. They are called rational domains. Are said to be rational or special if you don't want to give rational another occurrence in algebraic geometry, or special. And it is clear by the very definition of the topology on the spectrum that you have at each point a basis of neighborhoods which consist of rational domains. So they form a basis of neighborhoods on X. So you can really localize with affinoid domains. In fact, with those particular ones, they are not that particular because of the following theorem, which is the so-called Gerritsen-Grauert theorem, and which says that any affinoid domain is a finite union of rational domains. So you have basically an explicit description of a basis of affinoid domains. All right. So now what we have done up to now is to define a collection of distinguished subsets in the spectrum, and we have for each such subset well-defined affinoid algebra, and we want to see it as a sheaf. So because we have closed subsets inside the compact set, we cannot use the usual notion of sheaf with respect to the topology. So the right notion to use is the notion of a Grothendieck topology, but since we work with subsets and not with categories, it's quite elementary. So let me just give you the correct definition of the G topology on the spectrum of an affine algebra. So this is a very particular case of the general concept of Grothendieck topology. So the definition is the following. So let X be a set. A Grothendieck topology on X consists of what? Of two things, basically. First, you prescribe a collection of particular subsets, which you call admissible. So a collection T of subsets of X. So what you want to have, in any case, you have to have the empty set, the whole set, so containing the empty set. Containing X, and you want it to be stable by finite intersection. Stable under finite intersection. So those subsets, these subsets are said to be admissible. Are called admissible subsets. So you have a collection of subsets. In our example, it will be the collection of all affinoid domains in the spectrum. And what you want to do, shift theory, is to have coverings, to be able to localize and to glue sections. And so you prescribe for each subset in your collection a collection of coverings. So for each Y in T, a collection of Y of coverings, set theoretic coverings, I mean, subset whose union is the set Y. By elements, so you cover by elements of F, by admissible elements, admissible subsets, and you impose three axioms on this collection of coverings satisfying or such that. So first of all, you want that the trivial covering with only one element, which is y, is admissible. So y is such a covering. And you want two properties. Maybe you want to be able to restrict a covering to a subset. So say restriction. Which is to say that if you have two admissible subsets y and z with z contained into y, and if you have a covering of y, you want that the intersection of elements of the covering with z is a covering of z. So the restriction of y to z, which is to say the collection of all intersections, this should belong to the collection of coverings of z. So you're able to restrict coverings. And you want to be able to refine coverings. So sorry. This is script y. Where is the problem? Those here? Say, okay, let's call it V. Yeah, say V, Vi. So Y is the collection of subset which I call Vi. Okay? Is it all right? Maybe I don't want to give a name to the element of the covering. It's why I use script letters. And so you want to be able to refine covering, so refinement. What does it mean? It means that if you have an admissible subset, which and some covering of it, and each you have for any element of this covering a covering of the given subset. When you put all together the subsets, you have a covering of y. So if so we'll call it y v belongs to a covering of v for any v in y. So you have a covering of the pieces which cover y. Then the collection of all y v's is a covering of y. Okay, so this is the refinement axiom. And once again, so elements of cov y are called admissible coverings. So this is the definition. It's a bit long, but it's quite simple, in fact. And I can give you 3 examples which you can keep in mind. In particular, the last 2 ones, not the first one. So this is, in fact, a very natural concept. Look at those 3 examples. So first of all, you can start with a topological space X in the usual sense. You can take as admissible subsets any all the open subsets. So T is a collection of all open subsets. And what is an admissible covering? This is any open covering. You have an example of a situation in which all the axioms are satisfied. And in fact, this is the motivating example for the definition. But for us, it is not the nicest example we can think of. Another situation is the following. Once again, you start with a topological space X. And you take as admissible subsets the closed subsets. And for Y, a closed subset, you define the set of admissible coverings of Y to be the finite coverings, finite closed coverings, or finite coverings by closed subset. So this is another example of a rotating topology on the set X. You could even enlarge it and look at locally finite closed coverings. And in fact, if you look at the history of shift theory, at the very beginning, people were working with closed subsets when they were doing shift theory very often. And the third example, which maybe is intuitively is the closest to the situation we have in an Archimedean geometry, is the following. So, third situation, take X a polyhedron, and consider the collection of all subpolyhedra and for subpolyhedra of X, look at the collection of all finite coverings. So this is the so-called combinatorial version of 2. And from my point of view, it's very similar to what happens in non-Archimedean geometry, and namely it's very often useful to think of affinoid domains as spectra as polyhedron, and affinoid domains as subpolyhedra inside a polyhedron. Okay, but this is only an intuition. So now back to non-Archimedean setting. I will define a G topology on the spectrum of an affinoid algebra. So, okay. But before that, before I want just to say what is the sheaf on a space with a rotating topology. So definition, we have done what is necessary to define a sheaf. So let X be a set equipped with a quadratic topology T, so a pre-sheaf, say, of sets, but you can define sheaves of more general objects. A pre-sheaf of sets on X, so it depends of the topology, XT, is a functor from the category of admissible, so I will define it, admissible subsets opposite to the category of sets. So what is it? So functor F, where this is nothing but the category whose objects are the admissible subsets and the arrows are inclusions. Is the category with objects, well, all admissible subsets and arrows inclusion. So in more down-to-earth terms, what does it mean? It means that you have a correspondence between y in T, and so to y in T you associate a set Fy, and each time you have an inclusion, you require that to have a map in the opposite direction between the sets, with the compatibilities, because it is a functor, so composition is here, maps to composition here, so plus compatibility. Compatibility for Z prime in Z in Y. Okay. So this is a pre-sheaf, and a pre-sheaf F is a sheaf if you can glue sections with respect to admissible coverings. So if for any admissible subset Y, and for any admissible covering Y, script Y of Y, the diagram. So what you can do is to pick an element if in F of Y, map it to the collection of its images in the F of Z, where Z is an element of the covering. So this is so let's call it row. So okay, this is a restriction, so it maps A to A restricted to Z. So what you do is the following: you look at all the restrictions, and when you have an element here, you can look at the restrictions on the intersection of two elements, which are, so intersections are admissible because of the axioms. And you have two ways to do that. First component and second component. So you look at the product of all pairs Z prime in Y squared of F of Z prime. So you have two maps. This one maps the collection to the collection of restriction with respect to the first term in the pair, and the other one with the second pair. So a so if you have a collection here, what you do is you look at the collection of so B, where B index z prime is a z restricted to z inter z prime. This is the first map. And the second map, you do the same thing but with the second term. You map A to C, where C z prime is a z prime restricted to z inter z prime. Okay, so you have two ways to restrict to intersections, and you want this diagram to be exact. It means that this is injective, and the image is the subsets over which both arrows coincide. So this diagram is exact. Is exact, which means that f of y is the set of all collections A in the product such that when you restrict AZ to Z inter Z prime, this is the same thing as the restriction of AZ prime to Z inter Z prime for any ZZ prime in Y. And so this is a sheaf. This is the definition of a sheaf. Okay. So now I can come back to the non-Archimedean situation. So I will apply this general concept to the case of affinoid algebras and their spectra. So definition. Let A be a k-affinoid algebra. The G topology on its spectrum X is the Grothendieck topology and for this to have a meaning, I have to use a property which I did not mention, but I will just do it afterwards. So this is the Grothendieck topology whose admissible subsets are the affinoid subsets and admissible coverings are finite coverings by affinoid subsets. So if you want that this definition has a meaning, you need to know that the intersection of two affinoid subsets is affinoid, and this is indeed the case. So sorry? Yeah, sorry. Domain, you're right. Domain. Domains and domains. So this requires that this relies on the fact if V and W are affinoid domains, then the intersection is affinoid. and its algebra is nothing but the tensor product of the two algebras of V and W, whose algebra is A of V intersected with W is A V tensored over A with A W. So this is what you need to make the definition. And so let me conclude this section by stating the main result which underlies this definition. So there is a unique presheaf of Banach algebras on X, denoted by O of X, such that. So what are the sections on a given admissible? So this is a presheaf with respect to the G topology. So on A, so for the G topology. So what are the sections of an admissible subset, which is to say over an affine domain? This is nothing but the algebra which corresponds. So for any affine domain, the sections are the element of AV for any affine domain. V. And the restriction maps are the canonical maps you get between the algebras when you apply the universal property. And so the map from the sections of a V to the sections of a W, if W is contained in V, this map is the canonical map deduced from the universal problem which was our definition of affine domains. And so why is this interesting? This is because of the following fundamental theorem which goes back to Tate. And the theorem says that this presheaf is a sheaf. The presheaf of X is a sheaf with respect to the G topology on X. What does it mean? Explicitly, if you take for any V in X, which is M of A, an affine domain, and for any finite covering of V by affine domains, Well, the diagram. So what you can do is to go from AV to the product of the algebras AVI, and you can map to the product in two different ways of the algebra corresponding to pairs of indices, which is AVI tensor with AVJ. So this diagram of Banach algebras is exact. Is an exact diagram in the category of Banach algebras, which is to say that it preserves the Banach structure. So this is the so-called Tate's cyclicity theorem, and this is the reason why we look at collections of affine domains. This is bounded, and also the norm you get on this the image, which is induced by this norm, is equivalent with the norm on this algebra. Okay, so what I mean, this is not easy to prove, but one example is at least easy to consider. So look at the unit disk, which is to say the spectrum of the Tate algebra in one variable, and look at the following covering by two affine domains. So you can say that this is you can cover by a disk of radius strictly less than 1 or less or equal to 1, and an annuli. So R is any non-zero real number less or equal to 1. So this is an affinoid domain. This is isomorphic to the spectrum of the Tate algebra of radius R. And this is also an affinoid domain, which is isomorphic to the spectrum of the following Banach algebra. So you look at power series in two variables, and you mod out by this ideal. And in fact, you can easily see that this is the same thing as a ring of Laurent series. So where this ring of Laurent series, I can give you the complete description. So I say that R minus 1t Rs divided by Ts minus 1 is isomorphic to the ring of Laurent power series, so which is the collection of all Laurent power series with coefficients in K. And you want that the radius of convergence is exactly R in both directions. So there are, so to speak, Laurent series which converges on the circle of radius R. And so this is a finite covering of an affinoid domain by two affinoid domains. So this is a particular case of our general situation. And what is the theorem saying here? So what you say is that you can identify the algebra of power series with convergence radius 1 with the algebra of pairs f g, which are, so f is a power series which converges on the disk of radius r, and G is a Laurent series in this algebra. And such that f restricted to the, so to speak, circle defined by the condition that absolute value of t is r is the same as G restricted to the circle is r, no, r the same restriction. Yes? Ah, sorry. Yes, there is no. Sorry, there is no R. Yes, yes. This is intersection. Okay, sorry. Okay, sorry. Yeah, there is no R here. Okay, sorry. So here you impose convergence when n goes to infinity, and when it goes to minus infinity, you want to converge with this weight. Sorry. And the circle, so this is convergence on the annuli. And the intersection of the two is the circle. Okay, so E0R intersected with the annuli is the circle, which is the spectrum of the algebra I introduced. So you have a power series, a Laurent power series, and you want them to be equal in this ring of Laurent power series. This will just say that there are no poles. Okay. So if you write what it says, it's exactly the theorem of Tate in this situation. Okay, and just to finish with this section, this second section, there is a fact which is that in fact you can look at stalks of the sheaf. So you pick x a point. You can define the local ring at x as the inductive limit over any affinoid domain containing, so x is M of A again, any affinoid domain containing x, and you look at the following direct limit of algebras. And this ring is a local ring. So in fact, stalks of the structure sheaf are local rings. Okay, so I will not start the third session today. It will be tomorrow. I will give the definition of a general analytic space, but it will be quite quick. I won't give details. And then we will speak of curves. Maybe I can just rewrite this example correctly because it was it was a bit a mess, so what I did say is only the following thing. So look at this example more carefully. So you have y1, which is this disk, and y2, which is the annulus. So elements of the first algebra are just a power series. With the coefficients going to 0. And elements of the second algebra are Laurent series with coefficients going to 0 when n goes to infinity, plus infinity, and where the coefficients times r to the n goes to 0 when n goes to minus infinity. So this is the second algebra. And if you write the intersection, so the circle, so to speak, corresponds to the tensor product of the algebras. Yeah, sorry. Okay. Sorry, so the intersection is this algebra of Laurent power series. So you have an R both at plus and minus infinity. And what is the content of Tate's theorem here? Is that if you pick two elements F1 and F2 in the product of AY1 and AY2, so a power series and a Laurent power series, then what you get is that F1 converges on the larger disk of radius 1 if and only if it coincides with F2 in AY1 antecedent with Y2, which is clear because you have here a power series, here a Laurent power series, which are the good radius of convergence upper R, but so there is no poles because this is a power series, and hence it says that the radius of convergence of this power series is exactly 1 as you want it. So this is obvious in this situation. Okay, so I finished here for today.